So basically, sections 4-4 and 4-5 deal with confidence interval, and it can be confusing because a higher percentage of confidence usually means a wider spread in values. How many had a chance to look at these problems and do them? 4-4 and 4-5?
Not 4-5, just 4.
All right, well, I did post 4 problems for 4-5, didn't I? 1 month?
Yeah.
I mean, I wanted to make sure, now I'm gonna, before I do anything with PowerPoint work problems, I wanna really get this point across. I'm gonna start as simply as possible. Let's assume, for no other reason, other than it's simple, we've got some process X, and we know the actual mean value of it is 0, and the standard deviation is 1. That's about as simple as it gets. Now, 2 things from that. We know the density function for X would be equal to 1 over the square root of 2 pi. Normally there's a sigma here. Since sigma's 1, I'm not putting it in. exp minus x squared over 2. And that would be the density for those values if we assume a large number of samples, right? It's Gaussian distribution, right? If it was a small number, we would use student t, and I haven't given you any problems with student t, you kind of omitted it, because I don't know if your calculators can do student t. Has anybody looked at that, the t distribution? Yeah, they can.
It's TPF and TCF.
Well, there goes my case. I mean, if they can do it, I could hand out tables for this, but student t is real important when you have a small number of samples. And I call it the student t, it's just called the t distribution most of the time. Did you see the thing about, did I have the PowerPoint with how we discovered this? This guy, Gay Spear, named Gossett, who came up with this stuff working with some mathematicians. It's kind of interesting. But back to this. So if this is the case, we know the density function f of x of x. You with me? Now, if you take a look at this right here, I know if I want something, and I'll call it just capital F of x here, that's equal to an integral from minus infinity to x of that function, my f of x dx. And that tells you the probability of the value being between minus infinity and some value. Go with me to the area of the curve. Now, if we take f of x, and we go ahead and take it and we say it's going to be minus some k sigma, or minus k sigma, minus f of, actually, hold it. Let me do it this way. Since the mean is 0, I'm just going to put k sigma here, and then minus k sigma. And you'll understand why in 1 second, hopefully. So all I'm doing is I'm taking something, and I have a value, an odd value, of k there, and I'm taking it from here to here. This is going to be k sigma, and this is going to be minus k sigma. And the reason I'm doing this is because the mean is 0. Otherwise, I'd have to put the mean plus or minus those values. Now, I know if k is equal to 1, think about that. We did this, actually we talked about this. I'm really talking about the area here, k equals 1. Do y'all see that? And that actually means it would be 0.68 or 68% about of the area lies between those two values. So regardless, I mean, the standard deviation is 1, so I could make this just minus k to k, right? Now, in the confidence interval idea, we could say for this problem, if we assume sigma is 1, we could say that we were 68% sure that the value of the process or the random variable is going to be between minus, minus 1 and 1, pardon me. Do you all follow me on this? But if you take it to 2 standard deviations, I come out here, this would be minus 1. I'm going to try to make this a little better for you. So make this plus 1, minus 1. Now, if 68% is there, right, we would have a confidence that we have a 68% confidence that the value of the random variable would lie in this region, right? And obviously, the smaller or the narrower that region, the more accurate, or I should say, the less variation. Standard deviation goes down. It means the process has got less of a chance of being at any distance from the mean. That's the only thing I'm getting at. But you also notice, if you go to 2 standard deviations, right? Now all of a sudden, the percentage goes to 90-some%. Do y'all remember doing that? I forgot what it is exactly, but it's in like 93, 94%, right? And within 3 standard deviations, it's 99%. So we have a 99% chance of being between minus 3 and 3. But you see, as the confidence interval gets higher, the spread gets wider. It's an inverse relationship, and it's a little ironic, all right? So I'm 100% sure that the value of the process or the random variable is going to be somewhere between minus infinity and infinity. I'm not telling you anything of value. So here's sort of the dilemma. Normally, when I see stuff done, they use a 90% confidence interval, typically. And they can use 95%, but I'm going to tell you what happens is as you get closer and closer to the 100%, it gets so broad it almost loses value, because all these, the Gaussian distribution, it basically has almost no information, what they call in the tails. When you get past 3 standard deviations on any kind of real process that you're measuring, it's statistical noise. It's just the way it is. So with that in mind, and I hope this at least made sense to you, right? Now we talk about confidence intervals the way the book does it. And first we come over here and remember, I'm going to say that I'm going to take this argument, and what I'm going to do is say when I take the value of the mean of the process, and it's going to be mean of the process plus k sigma, and then mean of the process minus k sigma right here. If it's a true Gaussian, and I multiply this by 100%, and should be a little neater on this. This is what we call Q, and that's the confidence interval percentage-wise. So that would be the confidence interval in the book. He uses those. See if I get a better one. All these are kind of blood dry. That's better. All right, so this is the confidence interval, or how confident we are. Now this is for something called a 2-sided Gaussian distribution, or a distribution. We could use student t, it doesn't matter, but basically we're saying that value k there is associated with a q here. You with me? Now, you could actually figure this value out, because remember in the calculators, we did the inverse problem. If you basically had the value of you say you wanted 90 or 0.98 or something like percentage of the area of the curve to be below a certain value, and you wanted to know that value, you could use the inverse cumulative density function to get the value. I'm just saying it goes either way, right? So if I give you this, and I'm just going to say this, if I give you Q right here, you divide by 100, and then you can say if that's the case, now what I can do, well, I'm gonna do some of these problems, is basically because of the arguments of symmetry about the mean, if I knew the mean of the process, I can figure out the value of k that would be associated with this. We're gonna work some problems so you can actually see this. Now, I gotta say one other thing. He gives you some classic values for these things in the book. And let's see, for a, I'm not even sure what page this is on, but for a confidence interval, I'll put it here, of 90%, the value of k is, I believe, 1.28, and for 95%, better be sure about this, it's 1.96. I'm a little hesitant to say that with total confidence. One of the gaps that shows is right. I've been using these, but this is on page 172. I mean, 90 is 1.64. I'm sorry. Put 1.2 in my bad. And this is the value of k. So this is the value of q, and that's the value of k, and it goes on and on. There's a lot of values, but we can always calculate that value based on our knowledge of that right there. You're going to see we're going to go through that. What I wanted to do, and this is called the two-sided process. Now, if you think about the one-sided process just for a second, I mean, first, everybody follow me on what I'm talking about here? Basic idea of confidence interval, of Q, right? Now, if you talk about a one-sided, or the one-sided process, and this would be one-sided, and you take a look at the density function, now I'm going to be a little more exact. If this is the value of x, and this is the value of f of x, and this is the mean value, you know, it will look like this. The Gaussian will look like this. So with a one-sided process, if we take a look and we say we want a confidence interval of a certain percentage that the value will be greater than or equal to this value. Now I'm just going to show you this. So you come down here, and I want the confidence, my confidence in the value of the process being greater than its value. I'll call it A for no other reason than it's available. Well, what we're really talking about was the area under that curve, and then multiplying it by 100. That would be the confidence interval we have. Do you all follow me on this, class? So for this one right here, and now we can assume it's got a certain standard deviation. Here's the mean value. So what I have to do is, at least if I'm using the Q function, and yeah, I'll go ahead and do this. So, well, you use the cumulative distribution function though. So if I'm going to say it this way, really the area here would be 1 minus the area here. Does that make sense to everybody? All right. So I can say this area, for now, we're just going to use a capital A symbol for that. That area would be equal to 1 minus, then this would be the cumulative distribution function, or f of x. And then here you would have, inside here you would have the value A minus the mean value divided by the value of sigma. You follow me on this, Solomon? You agree with this, class? All right, that would be the area here, and that would be the probability of the value of A, of the process has a value of A or greater than A, or the random variable. Let me say it that way, random variable. I think we're clear on that, right? So what would the confidence interval be associated with that? Well, if you take a look at that, if we take yeah, it would be 100% right here, and it would be times that value of A would be the value of Q associated with that process. That's all really I'm saying about this, that's what it would be. And going back to this thing, if we had a two-sided process, right, then you could say that for a confidence interval, I'm sorry, a one-sided process, then the only thing you would do, it depends if you want a value greater than or less than this, is get rid of one of these. Either that one, or well, actually you get rid of that one right there for a one-sided process, and that would be the confidence you have. Now, let me try to say one other thing about this. I'm going to redraw what I drew there. So I got a mean value here of x, and here's the distribution function for my f of x. So before, we had a value here that was x bar minus some value k times the standard deviation, and it went up to x bar plus k times the standard deviation. And we could say between here and here, we're a certain level of confidence, right? Now, how confident are we from this value on up? Well, the only thing we do is get rid of this upper part, and I want to know how confident I am that the value of the process is greater than that. And the only thing you're going to do, and basically you can see that if you wanted a 90% confidence, right, that means the area from here to infinity would be 0.9, right? And that would be equal to basically a confidence K associated with that. I'm saying this. When you see some problems then I think it'll be clear. Are you with me on this idea at least? All right, now, if you did the problems, some of you at least, and I'll start with some problems in 4-4, just to make sure everybody's with me. I know last class, a lot of people are just, their minds were on the EMAC test, and it's understandable. So, I could pull up the PowerPoint, but I think I'm going to forego it. So, in this one, let's see. This problem. I think I did this one last time. Did we do 4-4.2? We're going to, yeah. If we didn't, don't worry about it. We're going to do 4-4.2, 4-4.3, and I want to make sure everybody uses their calculator so you can do this stuff without any kind of angst. If you want to put the values of, I can supply the values of K, but you can also get them yourself. And for this one, I'll leave that up there. So this is 2, and I'm not messing with student T right now. Can
Do you want exercise or problem?
Problem. I've got the exercises too, but I want to do
There's a problem here.
I've got the exercises too. Yeah, go ahead.
A very large population of bipolar transistors have a current gain with a mean value of 120 and a standard deviation of 10. The values of current gain may be assumed to be independent Gaussian random variables. Find the confidence limits for a confidence level of 90% on the sample mean if it's computed from a random sample size of 150.
Of what?
150.
All right. I didn't get into the more samples you have to take the standard deviation times K divided by the square root of n, but I'm about to. So there's some modification. The more samples, larger sample size, you have to take K sigma and divide it by the square root of the number of samples. Okay. So for this one, what they want is the limits, and to get a mental picture, what they're saying is, if we've got a mean value of 120, a certain standard deviation, they want to know what the upper and lower limits are here. So it'd be 120 minus k sigma over the square root of n, and the upper limit would be 120 right here, 120 plus, plus k times sigma over the square root of n. And this is simple, but what he's doing is, he's saying if we want 90% of the values of beta to lie in this range, and we want to figure out what that confidence interval is, the upper and lower part. With me? The only thing we have to do is find k sigma over square root of n. So if you take a look at this, for a Q equal to 90% here, K is 1.64, I believe, from over there, but we could calculate it too. And for that to be true, that means K sigma over the square root of n would be equal to 1.64 times the value of sigma, which he gave us 10, over the square root of, and samples are 150. Now, I don't know exactly what that is, but that calculation is really a straightforward one. You have 16.4 over the square root of 150, right? Can you give me that number?
1.34.
Everybody agree with that? I'm assuming he's right. There might be a few more numbers after that, but don't worry about it. It's good enough. Okay, so down here, if we take 120 minus that, what do you get?
118.66.
And this one, the upper limit?
121.33 or 34. Does that make sense?
That's pretty straightforward. That's 90%, right? Your calculators aren't even necessary, really, other than to punch some simple numbers, right? What about if I wanted the 95% confidence interval, what would happen to the lower part? The only thing would change is K, right?
Mm-hmm.
And K would go to 1.96, just for, does he ask that, by the way, for 90%, 95%?
It is not.
All right, but I'm going to calculate it anyway. So if we wanted the 95% confidence interval, here and here, now it would be 120 minus 1.96 times 10 divided by a square root of 150, and I don't even know what that is, but it's pretty obvious we can calculate it. What is it?
1.6.
All right, so this is 1.6, right? And if you take 120 minus 1.6, that's 118.4.
Mm-hmm.
I've got a point to make here, and the upper limit would be,
121.6.
pardon?
121.6.
You'll notice there's not a huge difference between 95% confidence interval and the 90%, very small. But when you get to 99%, now the spread becomes enormous because there's very little area in the tails, or we call them the tails. It's the things falling off past three standard deviations for sure. It just goes really broad. With me? So when you're using that term, or you read and hear about confidence, you've got to be a little careful, because a 99% confidence interval that our sample size, or the sample size justified our hypothesis, is really misleading. It means that you've got such a broad spread of possible values, just about any sample you'd be okay with. So just go with me on that. You'll see more. What's the next part of that problem?
Repeat part A if the sample size is 21.
Now, if it's 21, you have to use the student T distribution. I don't want to do that today. because obviously a lot of people aren't here. We've got, I don't know if they dropped or what, but I didn't see the latest class listing, but I didn't get any notification of drops. Is there something else going on today, another test or something?
There is a test, I don't know what class it's taking, I don't know what class it is,
All right.
but I know there's a test.
Who are we missing? We're missing quite a few. Tran? We're missing, what's his name? Is it Xander?
Yeah.
He's not here, that guy. All right, well. And what's the next, is there another part?
No.
Or just 21, we're not gonna do 21. That would be the student T. Student T, basically, everything's the same. The only thing is, now, when we calculate the spread, we have to use the student T distribution, not the actual Gaussian distributions. And that's basically it. We're gonna do the next one too, kind of quickly. Did I do this one last time or not? No? Okay, not bad. All right.
And we'd have to use the student T because it's less than like, I think it's 30 or 33, right?
Anything below 30, you have to use student T. But the thing about the student T distribution and the Gaussian, as the sample size gets large, they overlap. It basically, one becomes the other. And so the obvious question is, well, why don't we just use the student T? I don't have a good response for that, other than the fact is it's more complicated to calculate for there's something called degrees of freedom that have to do with the number of samples. And they're called gamma functions. In the old day, you'd have to actually calculate the gamma function. There was a recursion relationship, and those things are irritating because we have tables for that. And I don't even make you use tables, but I think, does anybody know if Bashir requires tables usage or not? Nobody? I'm curious, does he?
Yeah.
He makes you use the tables?
Yeah.
Oh, I hate that. I hate that the calculator is the reason you don't use, if you've got a good calculator, you don't need it. All right. 4.3. Problem 4-4.3.
Repeat problem 4-4.2 if a one-sided confidence interval is considered. That is, find the value of current gain above which 90% of the sample gains would lie.
Okay. Be attentive here, because on a quiz on Friday, something like this may appear. Got my gist? All right, now, hear me on this one. First, everything's the same. We've got a value, the mean of beta is 120, right? Standard deviation is going to be 10, and n, the number of samples, is going to be 150. So all that stays the same. With me? Now, here's the difference. Now we come over here, we take a look at this Gaussian profile. We got 120 as the mean, and we've got this. With me? Now, it's the one-sided confidence interval, so we want to know where the lower limit would be here. This is our question mark, we don't know yet. So that we have 90% of the area. They want a current gut, does he say one-sided for beta greater than, or?
Value, the current gain is above 90%, which is sample gains we want.
Above 90%, yeah, everything's 90%. Basically, the current gain is going to be at this minimum or greater. That's what they're looking at. So we're going to calculate this value, just to make it clear. This is going to have an area of 0.9. And now, I think everybody's with me, that's right. So what does that really mean for us? And if you take a look at this, I think we should use I'm going to use the normalized values of this because it'll be easier, I think, for me to explain and you to do. So I'm going to take this whole thing and I'm going to go, and I'm going to create that variable z that's equal to the actual value I want here. Well, yeah, I'll just call it X here. Or I should, no, we're using beta, make it beta. And so we want the value of beta minus the mean value, which is 120, over, now here's, it's a little tricky. Here, the standard deviation enters in, but we have a whole bunch of samples. So the standard deviation is 10, but we have to divide it by the square root of the number of samples, which is 150. You follow me on this? Now, the reason I'm showing you this value z here, first in the book he uses discussions with that symbol and this kind of thing. But what I'm really doing here is saying, I have this function q of z, and that's equal to the integral from z to infinity of, and this is the normalized density function, because this gives rise to a density function, an fz of z equal to 1 over the square root of 2 pi. You get rid of the sigma, and it's times exp to the minus z squared over 2. That's the normalized density function. So it's the integral of this and we want that equal to 0.9. You always doing this? Now, for you, you would say that your, and I'll use this symbol, is 1 minus this, or 1 minus 0.9, or 0.1. Just remember, you have the cumulative distribution function, and what this is the cumulative distribution function of z, and the mean value here is, or I can use u because that's what calculators have. U is equal to 0, and the standard deviation for this is 1 for this particular thing. Can you all follow me on this, class? This is how we did some problems a while ago. And I want it equal to 0.1. Now, your calculators can do the inverse operation, can't they? Mm-hmm. And tell me the value of the argument here of z that will give me that.
Negative 1.282.
Minus what?
1.282.
Anybody confirm that?
Yep.
Minus 1.282. So now I come over here, right here. Y'all with me? Now I'm going back here. I've got this value. I'm going to calculate that lower value beta now. I think you follow the logic, but let me do it right over here. So I have minus 1.282 equal to beta minus 120 over 10 divided by the square root of 150. And I'm going to just write this down here. So I'm going to have beta, or the lower value beta, equal to 120 minus 1.282 times 10 divided by the square root of 150. And I don't know what that is, but.
I got like 118.95.
What is it?
118.95.
So this value would be 118.95. And is that the answer? I don't know, I'll write it down, but. $118.95. With me, we got it? You everybody follow me on? I did the normalization to get that value. Now, there are k values for one-sided. But you see, we didn't have that k value available, so we had to calculate it, basically. With me, class? And I can tell you also one other thing. If you got a two-sided distribution, and you want the area in here to say be not, let me make that point a little clearer. let me do it right here. Just give me your attention for this part. This will help you a lot. Once you see what's really going on, a lot of this just becomes simple. But until you do, you've got questions that you don't know what questions even to ask about these things. And they will drive you a little nuts at first. So, and keep this in mind. If you think about something where we have a process and we've got a mean value here, and I want the spread here, call it x bar minus, and it's really going to be k sigma divided by square root of n here, and this would be x bar plus k sigma over the square root of n right here. With me? I'm going to try to make sure I say this right. You know, for any confidence, say I wanted the 93.5% confidence. With me on this, class? So that means, I take back, make it easy, 94%. So I wanted 94% for the area in here to be equal to 0.94. With me? And I asked you what the limits are, upper and lower limits. Now, hear me on this. Got that? Everybody follow me on this? That means I've got 0.06 of the area outside that, right? But it's symmetrically distributed between the mean. With me? That means here in this area would be 0.03, and then the tail here, it would be 0.03 as well. With me? Now, think about this. If you remember how I normalized just a second ago? If you do the normalization, right? What I'm really saying is if you do basically this, where you would have x bar, remember this value z is the critical one, so let me be real clear about this. For this particular process, and this is the critical part right here, this area, on your calculators, you can give me the value of z that would be associated with a cumulative distribution equal to 0.03. With me, class? I don't even know what it is, but we might as well just write it down. So this value of z would be, and set the cumulative distribution equal to 0.03. It's going to be a large negative value, but I don't know what it is. And it assumes sigma is 1 and the mean is 0.
I got negative 1.88. I did the
Minus
inverse.
1 point what?
0.88.
Anybody confirm or deny? All right. Now, regardless of anything else, if I know that point, right? If we got a certain number of symbols, now I come over here, and I'm assuming you know the mean value, and you know the standard deviation in number of samples. If you didn't know the standard deviation, it would be the standard deviation of the sample spread. You would take the samples and you would find the variance of the samples, remember? And then you'd use the unbiased estimate of that. And then you would take that value and divide by the square root of n. So if you don't know the actual true variance, you use the variance of the samples. That's what I'm really getting at. And when you do that, you can actually work back to that value. Might as well just complete this idea. So we've got this value for z, and I know that value is equal to minus 1.88. Since I use x there, that's going to be x itself, the value I want. I'll call it x critical. You'll see why in the next section. It's minus the mean value, so I have to give you a mean value. Let's give you a mean value of 20, just for the heck of it, of 20. And let's assume the standard deviation is 5. Just making up numbers, and the number of samples is 100 to make life easy. So now I have x critical minus 20 over The standard deviation is 5 divided by, the square root of 100 is 10. Got me, everyone? I think you guys get this, right? What I'm doing? So that means when I go down here, I have, I'm gonna have, what is it, 1/2 of 1/2. Minus 1.88 times 1/2, and this is gonna be plus 20 on this side. Is x critical? Can you tell me what that is?
19.06.
And I had a mean value of 20, and this would become 20. And this here, this value would be 19.06. And since we have, by the way, since we have this, which is going to be 1.88 divided by 2, we can add that to 20 and get this value as well. Follow me? And that's sort of a way to do that. For we did it for one side, we could do it for two sides. If you didn't have the value of k, you can do it that way. All right. For 1.43, for 4-4.3, was there another part to that?
No, that was it.
Okay. You can see it's really fussing around with the density functions. Now, that's all in section 4.3, and I don't think there was all the other problems, I think in 4.3, I'm sorry, 4-4, basically, yeah, there's only 3 of them, but the third. All right, now we're going to move into 4-5.1. And I guess most people didn't look in section 4.5? No? You did? Okay, good. Well, here we go. We're going to have, it's called hypothesis testing. Now, we first are going to have to understand this confidence interval pretty well. Then we're going to say if we do measurements and we get a certain value, does that value validate or invalidate a statement? Basically, are you within or outside the confidence interval? That's the only thing this section is doing, but it's important to have a good appreciation for what they're asking. I'm just going to put the PowerPoint up on this one, but I think I'm just going to go right into problems. Let's try this. So for this problem, I really think this is the best way to do these things is, explain the application of theory, because the PowerPoints, Denny's PowerPoints do a good job. He uses capital H0 and capital H1 for either it works or it doesn't work. That's my translation of his things. There's a conjecture. This is called the scientific method, I believe. And you're supposed to, if you're doing your doctorate and stuff, if you have anything where there's experimental measurements and you want to see if in fact the theory you do confirms or denies it, you have to use this. So basically you say, I make the statement this process is 95%, is going to have a confidence interval of like 95% of the value of, say, beta is going to be greater than 180, something like that. And I make a statement that the standard deviation of this should be 5 and the mean value should be 121, something. I'm going to say this is my conjecture. Now I do measurements. And I find the mean value or mean and standard deviation of my measurements. And I have to figure out if they confirm or deny my conjecture. Got me on this one? So that's where we're up to. For this one, what does it say? And I'll show you what it would look like.
The resistance of coils manufactured by a certain company.
Oh, is this, how many samples are there?
9.
Oh, that's student T. Go to the next one. I think I actually changed the next one to have, what is 4 dash?
5.2 has you repeat 5.1, but n is 50.
Ah, perfect. So, n equal 50, which means Gaussian. That's student T. We'll do student T on Friday, probably, but I want to make sure I cover this stuff with Gaussian. Go ahead.
Claimed mean of resistance of 100 ohms.
Okay, wait, they claim the mean value or of the resistor is 100 ohms. This is the claim. And,
The sample mean is 115 ohms.
no, but what is the standard deviation?
Oh, the standard deviation is 10 ohms.
10 ohms? It's a big spread. Okay, that's the claim. Go ahead.
And the sample mean is still 115 ohms.
And what's it?
The sample mean is 115 ohms.
Wait, we've got n is 50, right? All right. These are the claim, right? I mean, this, so, and what does it say in the measurements now?
The sample mean is 115 ohms.
150.
115.
Oh, 15. All right, so our mean of the sample is 115. Go ahead.
That's it.
And they want to know if the claim is verifiable, right?
And I justified at 95% confidence and then 90% confidence.
All right, so Q equals 95%. And for that, for 95%, K is 1.96. With me? I mean, I'm going to just tell you that. Yeah, I would give you this, but I'll give you like K of 90, 95. If you needed a value of K for like 99, I would give that to you. But this is a two-sided value, remember, not one-sided. And that's important. So we want to see if the claim's valid. Here's what you do first now. We're going to find out what's called the critical value, Z critical. Okay, now, here's what we do. Here's how I go about doing it, the way I think about it. I'm going to say that if I want 95% confidence interval based on this, on the information I have, that being the standard deviation, and we got, how many samples? We got 50. So here, I'm going to take R bar sample minus R bar over sigma divided by the square root of 50. Well, actually, here's what I should do first of all. Make sure you guys see this. If I take a look at this, and the mean value is 100, the standard deviation is 10, I know that this value would be 100, and it would be plus K sigma divided by the square root of n, and this value would be 100 minus K sigma over the square root of n. First, you all with me on what I'm showing you here? That would be 95%. If this is the claim, and we have a sample size of 50, then tell me what K sigma over the square root of n is. K is 1.96 times 10, so it's 19.6. Divided by the square root of 10,
Screw it, you mean screw root of 50?
what's that?
It's, I got 2.77.
That means the lower part here is gonna be 97 point something.
0.23,
What's that?
97.23.
Okay. And this point?
102.77.
Okay. And this would be 95% of the area. Now, the value that he gets, we're gonna see. Actually, we don't even have to do that calculation directly, do we? He says his mean is 115, and that's way out here. And that's outside the bounds, with me, class, without even a calculation. And you know, so it doesn't meet it. I'm very curious, is there a misrep somewhere there? Because that's way outside the bounds, it's not even close.
Well, they don't fall into the confidence intervals at the end.
Huh?
They don't fall into the confidence intervals, so maybe that's kind of what he's trying to point to.
Yeah, it exceeds it by a huge margin. I just looked, I put a solution up there. I don't know what the solutions manual says, but that's an extreme. I mean, it's not like it's close. Usually these problems are close. What I really wanted to get at is, I got this just from the information he has, the standard deviation, the mean, and the number of samples. So that's the range of 95% confidence. Now, if you do a measurement, you get a mean value inside there, it's possible. It's not a worrisome thing. But if you get a mean value outside of there, and 115 is not a little bit, it's like way outside there, it can't happen, right? However, here's a question that I could ask. I'm just giving you the theoretical. Now just listen. If I wanted to know what confidence interval I would have to be at in order to allow this, with me? How would you do that problem? You remember, the bigger the comp, if you get 99.99%, it gets very wide. How wide, how much wider would it be? How would you do that?
You'd set the Q to 95% sulfur.
Not 985. You don't know what Q is. I'm saying I got this value, right? I mean, what do we always do? What did I do up there? You would take that, you basically use 115, right? Follow me on this one. For yours, actually, you know why? You have that cumulative distribution function where you can put in the, I don't know, can you do an inverse on that one too?
Yeah.
All right, just listen to me now. No, hold it. The cumulative distribution function, right? It's going to be the integral from that thing all the way up to this point, right? But, I mean, up to, say, let me say it again, because I want to show you how you would do it on yours. We're going to do that problem. If I have a value of the mean here of 100, and a standard deviation equal to 10, and I want to know what confidence interval. Remember, I want this. Now, here's what I'm going to say. Well, I know from here to here, if I have, there's a certain percentage, right? But if I have 115 here as a value, I would have the area integrated from here all the way up to this point, right? Now, I could say 1 minus this area would be this area, right? But the actual, you have to understand me on this one. What I really want is the area in here. So if I could calculate the area here, and you could, right? Take 1 minus the cumulative distribution function, where you would have 115 as the upper limit, the mean of 100, and a standard deviation of 10, right? You take 1 minus that area, then you get that area, right? Then if you take that area times 2, you'd have the area there and there, right? 1 minus that would be the area here, if you get me on the way I'm thinking. And if you multiply that by 100, you'd have the confidence interval. Does that make sense? So let's do this. We're going to calculate the area up to 115. So I need for you guys to do this cumulative density function of, here it's going to be, the value is 115, the mean is 100, and the standard deviation is 10. And that is going to be, just store that number, but it's going to be an enormously large, it's going to be very close to 1. Because we're going to take 1 minus this in 1 second. What did you do? 0.933. Anybody confirm or deny that? Is that right? Oh, hold it. I forgot to enter in the value n here. So if n is actually 50, then the standard deviation you put in there would not be 10. It would be 10 over the square root of 50. Can you follow me on the reason for that? Because we've got 50 samples. It's going to be a lot bigger than that. My bad on that.
Drew, which one are you using? The normal studio?
Yeah,
What are
Say
the
again?
pounds for
I
that?
got 1.
What?
I got 1.
me too. I got 1.
So it's basically, you would have to do more decimal. You would have to have a more precise, higher precision in your calculators. It's so close to 1, it's basically saying it's like 99.999% of the area. So really, I couldn't use that value, but you got to understand how crazy it is. This thing is so far out of the range of the possible because the standard deviation is 10 and we have 50 samples. It's like, no, basically it would take an infinite, you would have to have almost 100% confidence interval, which goes to infinity. With me? All right, forget that part anyway. But I mean, if I had something a little more reasonable, like instead of 115, I had 105, then you could go through, just for curiosity, I'm going to say this is 105. 95. And what do you get for that? That can't be that bad.
3 nines and 7.
What?
0.9997.
Okay. That's all, 0.9997. All right, now take 1 minus that and multiply it by 2. Actually, let's see.
It'd be 4.07 times 10 to the negative
All right, multiply that by 2 and subtract it from 1.
I think that's what I'm saying, is the final value is
40.
4.07 times 10 to the negative 4.
Say it again.
4.07 times 10 to the negative 4.
Is the value of this.
The whole. value.
This?
The one, yeah.
Mhm. Just multiplying by 2 is the 0.00. So inside the
Or you're
parentheses,
asking for the.
and then you gotta do 1
bigger
minus
side of
that.
it.
So
0.9996.
you need to subtract.
0.9996, right?
Yeah.
That means the actual confidence interval will be 99.96%, which is immense. And it obviously shows you why the higher confidence interval doesn't really tell you much. You want confidence intervals, normally I think it's 90% is the one that's always used, because that tells you something about the bell curve, that you are basically within 2 standard deviations of the mean. And if you're in a 90% confidence interval and your values are falling in there of your actual measurements, then you're good. Your claim is true. That was 5.2, and I think for 5.3, I did this problem, but I made the sample size larger. Hold on for 1 second. That's the one again.
5.3 is the MATLAB one.
Or 5.4, pardon. If you go to 5.4, is this 5.4? Okay. I bumped that sample size up to 40, and that way we can use, what was it, 50? We can use Gaussian. Hold on for a second. Yeah, I use 40 samples for 4.54. I want to put this one up here and do it because it's a one-sided confidence interval, and it's going to see if the claim is justified or not justified. Hang on for 1 second. Get this done. Matter of fact, I'm going to set this up, and I'm going to have you guys tell me what. I think you get it now. Remember, the way I always do these things, first I start with what the claim says based on statistics. Remember, the whole idea is if you know the mean value of the claim, the standard deviation of claim, and the number of samples, you can go ahead and you can figure where that lower point is on the real curve. You all with me? Now, after that point, the lower or and upper, now you see what the measurement suggests, and you see if you are or aren't inside that area. That's the big deal, but we have to be more precise with the values we use. So for this one, this is a traveling wave tube. Forget about that for now. He has something where he gets a mean value. This is the true mean of 4 years, right?
Yeah.
And then he has a standard deviation, true standard deviation of
1 year.
1 year. That is an enormously broad standard deviation, by the way, for something that has a mean value of 4 for a traveling wave tube, because that tells you terribly unsure about how long it's going to last. So then he's going to go ahead and he puts a bunch of these tubes. I think he says like 20 or something like that in there. So it's got 21 degrees of freedom for those of you who are interested in the student T. Don't worry about that yet, but we're going to, I made it 40. So now I say my sample is 40. Got me on this one? So we're going to first set up what that should look, and he says one-sided, doesn't he? Or he says value.
The mean lifetime is at least 4 years.
Yeah, so greater than, this is a one side. First, on this one, get an idea of what he's talking about. For these values, out here, he's saying it's 4 years, so the mean value's 4. And it's got a standard deviation of 1 year. It looks like this. I mean, that would be the density function, my f of x looks like this. Then he says, is it a 90 or 95? Yes, sir.
I'm just got a quick. It says it's the standard deviation of the sample. So does that matter? Because I thought it was like the sample deviation
Yeah,
is
but
different.
if you don't have the true standard deviation, you use the sample standard deviation, that's
Mhm.
S, and you still have to divide by square root n.
Okay.
But we're gonna go ahead and take a look at what these, what his claim means in terms of the distribution he would have available with me. It's a one-sided, right? I mean, it's basically, the claim is, he's gonna have values equal to or greater than 4 years.
Yeah, at least 4 years. Yeah.
All right, so no matter where you are, you think about this here, doesn't matter if you're above or below, but call it this value right here, he's saying that he's got a certain level of confidence or a certain area, the area that I'm showing you hidden would be associated, that area times 100 would be the confidence he has in the values, with me? So, if the mean lifetime, no, listen to me on this one, if it's 4 years, then there's a 50% chance that the true value of the bulb, or whatever you call it, the traveling wave tube, is going to be at least 4 years or greater, right? But there's also a chance it's less than that. Follow me? And the further down I go, the larger the chance is that it's going to have that value, right? It'll be within that range. So we're going to calculate this range right there, the lower limit for, is it 90 or 95?
90%.
With me? So we want this area here to be equal to 90% of the total area, or 0.9, and this is a one-sided, remember, right? Now, you got to get the standard deviation, so he has standard deviation of the sample, but what it would look like is this, it would be S like that. That would be the standard deviation of sample. If it was S tilde squared, or S tilde squared bar, that would be the actual variance. But he gives this as 1. So that means when we look at this, we're taking a look, and since this is really, that area is 1 minus the cumulative distribution function, right? Everybody with me on this? So if I take a look at this, what I'm going to do is say, and I want this value x here, and I'm going to show you what that value is associated with. I'm going to take 1 minus, and this would be your cumulative distribution function here. And I want the value of that x with a certain mean value, and the mean value is 4. And the standard deviation would be 1 over the square root of 40. We've got this solution online. This right here would be equal to 0.9. And to be frank about it, that means I would say the cumulative distribution function for x, 4, and this is the mean is 4, and a standard deviation of 1 over the square root of 40, right here, would be equal to 0.1. You agree with this, class? Just switching things up. So what I need to know is that value of x.
You just do the 0.1 is equal to,
I can normalize it if it makes it easier for you. If you want me to, I will. I think yours can do an inverse of this, can't it? All right, what do you get for this? Are you with me? I could use that normalization and do the whole thing.
3.79.
Anybody confirm that? Pardon? Is that right?
I don't know.
How many know how to do this on your calculus? You do. You just gave me the answer, right?
Yeah, I did it with 0.1.
What?
With 0.1. The inverse normal?
Well, I had 0.1 as the value of the cumulative distribution function. What I need is the value of x associated with it. If the mean is 4 and the standard deviation is 1 over square root of 40.
Oh, yeah.
I don't know if it's 3 points. It might be.
I got 3.7 or 3.8.
Yeah.
Right.
We'll go 3.8. Okay, I'm going 3.8. So this is 3.8. Now, everything else has to do the measurements, the actual measurements of the mean, fall within this range. And if they do, it confirms. If they don't, it denies. Does this make sense to everybody? All right. Now, what does he say that the value of the measurements are?
It is found the mean lifetime of the sample is 3.7 years.
So the mean lifetime of the sample is 3.7. 3.7 is below that range, so it does not confirm. Y'all with me, class? In other words, that claim can't be used. The 90% claim. You with me? So a logical question, now hear me, a logical question, you might appear on a quiz, would be what confidence interval would be needed to allow 3.8? Follow me? And how would you do that? You got it right there, right? So what are we gonna do? Remember how I had that at 0.1 was associated with 90%, right? So now I'm gonna go ahead and simply take this and make it 3.7, because that's the value we're given. Follow me? You guys have this, now it's a direct calculation. And you're gonna give me this value. I wanna finish this, I'm 1 minute over, but you all follow me. Just, you got your cumulative distribution functions, right? So what is this value? It's gonna be like 0.7, 0.5, something like that, or 0.05, pardon me. Remember, use the same standard deviation, 1 over square root of 40. You got 3.7 here instead of x. And what do you get for this?
0.03.
0.03. Anybody confirm or deny that? You get it? Guys, you with me? I want to make sure these guys are. You good? Good? Think so. That always scares me. Yes. Whenever you're doing military testing of weapons, you know, I think that's right. It doesn't work. I've watched mistakes happen, literally, with big cost experiments. All right, now, for this, what is the confidence interval? It would be 1 minus this. So 1 minus 0.03 would be 97% confidence interval. So we have to go to 97% confidence interval to say that that test or this measurement would be. But you can see how that's misleading. Got me on this, guys? Mm-hmm. So that's why I say 90% confidence interval is the thing probably almost everybody uses, and for testing and polling and all that crap. And the next section in there, give me 1 second. I want to make sure. First, I've got the solution for this up there for 40. I'm not going to get you on student T distribution, but I might have to do it on Friday just because it is valuable because there's so many times you can only do a small number of tests and you can't do a large number of tests on samples. It's just the way it is. But the next section is going to have something called linear regression. Do you know what linear regression is, guys? All right. make it real simple. You got a bunch of data. You got X versus Y data. You do measurements. For a given value in X, you get a measurement of Y. Given value of X, measurement of Y, right? Now, the linear regression curve, say, what if we wanted a straight line to be a best approximation for that, right? Which seems stupid, because you would normally, if you really want to approximate things, use a polynomial fit. But the reason linear regression is good is because there's a metric that they use, and it's for the level of agreement the data has, and it's called the R value. Now, I'll get into that in a second. But if you wanted to do a straight line through there, well, you would write the equation y equals mx plus b. That's just a straightforward thing, right? Now you've got data samples, and for each of these samples, you're going to have a value of d of I. Then, remember, I should put up the PowerPoint of this. What you want to do is all these measurements, you know there's a straight line that should be there, but you're going to take all these measurements you have, and you're going to try to minimize the error and find the value of m and find the value of b. Remember, y equals mx plus b, slope plus intercept, that would minimize the error between them. And that value of m and b are something that you calculate using what's called linear regression. Now, your calculators do this in a heartbeat. That's the reason I don't need to have you go through the entire calculation. But there's one thing you have to appreciate. It's on the PowerPoint. When you do this at the end, once you get all this information, there's a value of r. And if a closer r gets to a value of 1, the more it is a straight linear relationship. With me on this, class? And it will have a positive and negative value. A negative value means as x gets larger, y gets smaller. It's inverse. Positive value means, in general, it's increasing for the value of x. And if it's got 0, it doesn't really mean much, because that could mean it's just scattered all over, or it's a flat line, one of the two.
Mm-hmm.
But that's there's all sorts of ways to do this. I want you to be aware of it, but your calculators will do this. You really don't need to be an expert in how to do linear regression programming or anything, because to be frank about it, it's like using a slide rule for calculations. That's the reason the calculator's there. You don't have to use a slide rule or pen and paper to calculate all of that. Where we're going after this, and that little spiel is, I'm supposed to cover this material, so I'm just covering it, sort of. We're going into chapter 6, and this is going to be an important chapter. It has a lot to do with some higher level mathematics, but it has to do with autocorrelation, correlation, with something called the spectral energy density. And this is my area, so this is something I really kind of dive into, but I'm not going to make it hard. So for Friday, section 4.4, section 4.5, got it? Make sure you know. And we'll see you then. I put up some problems. I'm not going to ask you anything crazy, but I'm kind of, and I'll put the values of k up for the two side, or I'll give you those values, but you should at least have enough faith and understanding to go back and calculate the value if you need it. Now remember, here's the mistake that's usually made, not taking the standard deviation divided by square root of the number of samples. That is always a concern, and it's always something that crops up. Because whenever you're doing sampling, it increases the actual, or it changes the true variance. That's one of the square root. All right, I hope, did you guys understand where it's going to get at? It's nagging for me to do this. If I just use the formulas, I won't understand what the heck's going on. Anything profound today going to happen, like rain? I think, isn't it supposed to rain today too, or am I wrong?
It's supposed to rain like every day.
Yeah.
Probably could pop up.
So when's our last day of class? Is it 29th?
30th or 31st. It's whatever the last day of the month.
Yeah, I think it's 31st.
Huh?
You know what I'm saying? Okay.
So we
James,
got,
or-
Yeah, it's that Friday the 31st.
so we have what, 7 class days left?
something like that. 1, 2, 3, 4, 5, 6, yeah, 7.
We got Friday, or 7 class days.
No,
We're gonna get through the autocorrelation and the spectral energy density now, but that's, some of that gets a little bit more difficult.